You know, another reason we don't do a lot of group work is just because of time. It's really it's really difficult in a course like this to slow down. Like in developmental math classes, they love group work because the curriculum is not truly set. It's not like a course like this. I've got to get you from point A to point B, or else in Cal 2 you'll be too far behind. So we don't have that flexibility, and unfortunately the state has crammed way too much information into what a calculus sequence is. I mean, if to do this correctly, we need at least Cal 1, 2, 3, and 4. 4 4-hour courses, we could do it. But we're doing our best with what we've got. So so how do we move on? Should we? No chanting? No? Anybody want to light a candle or anything? No? All right, so 3-7. Let me bring up the notes on 3-7. Let me see. 3, 4, 5. No, 3, 4. 3, 4 we're not. 3, 4 is exponential growth and decay, and that's college algebra stuff. Yeah. Okay, so here are the notes. Let me zoom this up. Can't really see this. Can everyone see that okay? All right. So in pre-calculus, the course before this, right, you studied, there were 6 trig functions, right? Sine, cosine, tangent, secant, cosecant, cotangent. We already know the derivatives for all of those. We did those already, and we have them on the formula sheet. But then in pre-cal, you also studied the inverse trig functions. And since the inverse trig functions are trig functions, or are functions, they should also have derivatives. And so this section is about establishing the derivatives of the 6 inverse trigonometric functions. And so these are all on your formula sheets, but I have them also here in your notes. And so what I'd like to do is I'd like to take some time to establish maybe where 1 or 2 of these come from, and then we can use them to apply like chain rule and product rule, and it just opens up again more possibilities of things we have to take derivatives of. So let's start with this first one. Y equals arc sine x. Maybe we should do a little refresher or not on what the arc sine function is, or yeah, you want to do a little refresher? All right, so remember this. Back in Cal 1, I'm doing this in red. When we define the sine function, we had this sine curve look like that, and it went in both directions forever. Yes? We said it was a function because it passed the vertical line test, but it failed to have an inverse because it failed the horizontal line test. So what we did was we got real clever, and we cut off the domain of the sine function. That's supposed to be vertical. Right here, and we just said, forget all this other stuff. Just look between negative pi over 2 and pi over 2. If you just look at the sine function in here, it's still a function, passes the vertical line test, and passes the horizontal line test just on this little piece. And so we define its inverse function just by cutting this one in half. Does that kind of ring a bell a little bit or no? Okay, so what we did is we said take y equals sine x on the interval where x is between negative pi over 2 and pi over 2. If we do that, then we can define a new function called the inverse sine, which basically goes in there and undoes whatever sine does. And it's going to have a domain that's between -1 and 1. So let's see if you remember this. If you have a sine function, when you plug a number into the sine function, you're plugging in an angle, aren't you? Like what's sine of 30 degrees? And it spits out an answer, doesn't it? And that answer is between -1 and 1. When you're working with an inverse sine function, you plug in not an angle, but a what? A number between -1 and 1, and it spits back what? The angle it came from. So it's going backwards, right? So we already saw that when you look at the sine function and you take its derivative, it gives you the cosine function. What we're going to say now is this arc sine function that we defined in pre-cal, if we can graph it, what does its derivative look like? Or what does the slope of a tangent line on that curve look like? So what is it according to what I wrote there? Well, what is it? I don't have it here. What is it? 1 over the square root of 1 minus x squared. That should be very strange. The derivative of sine was cosine. You would think maybe that the derivative of the inverse sine or arc sine would have something to do with sines and cosines, but it doesn't. It has like this weird 1 over square root thing, right? So where does it come from? Let's see. That's all I was doing to review. Was that okay? Just as like brief little. Okay, so if y equals the inverse sine of x, or what's another way we write inverse sine if we don't want to use a little -1? Arc sine, you just actually write arc sine x. I hope everyone is aware that these two mean the same exact thing. Then let's show that the derivative of this, the derivative is 1 over the square root 1 minus x squared. Let's show that that's true. So how in the world are we going to show that? Well, here's how. Let me start off with the original function. What I'm going to do is I'm going to take the sine of both sides of this equation. So I'm going to take sine of y, and on the right side, sine of arc sine of x. So I'm not multiplying both sides by sine, right? Sine is not a number. I am taking sine of both sides. Does that seem like a legitimate move there? Take the sine on both sides of the equation? Seem fair to you? What does the right-hand side spit out? What happens if you put sine together with arc sine? They cancel out, right? Because they're inverse functions. They undo each other. So what falls out of the right side is just x. And what's on the left side is sine y. We okay with that? Remember, our goal here is to figure out what the derivative of y is, right? What's y prime? So right now I have a new equation, and what I'd like to do is this. What is that? I'm going to differentiate implicitly with respect to x. So what is the derivative? What is the derivative of sine of y with respect to x? I saw this major problems with this still on the test, implicit differentiation. So first start with sine. Derivative of sine of something is cosine of it. Anything else? Times dy dx or y prime, right? Because then you have to go inside the sine function, take derivative of what's in there. Derivative of the y inside is y prime. Anything else on the left side? Okay, so left side's done. Equals, what is the derivative of x with respect to x? 1. So that means that y prime, if I divide both sides by cosine y, is 1 over cosine y, isn't it? What is 1 over cosine by definition from pre-cal? Secant. Hey, I've got y prime. But that doesn't look like the answer, does it? 1 over the square root. Well, the problem is that right now our answer has y in it. We'd like for it to have x. All I need to figure out is what is secant of y. So I'm about to show you something. You did it in pre-cal. I hope your instructor stressed it to you. These things called reference triangles, where you draw a reference triangle, a right triangle, and you create these relationships between the sides. I'm about to do that, and it comes up again in Cal 2 quite a bit. So I just need to figure out if you agree what secant of y is. I'm going to come back to a piece of information that I had that connected y and x together. I know that sine of y was x, right? That's the thing that I differentiated. I'm going to draw a triangle that illustrates this relationship right here. Here it is. And you just tell me if you agree with this or not. If I call this angle y, call this side x and this side 1, then what is sine of y? The angle's y, right? Sine of y, sine is which side over which side? Opposite over hypotenuse would be x over 1. X over 1 is x. So do you agree that this equation corresponds to this triangle? Yes? So sine y equals x over 1 is what this is saying. And from that, I drew a triangle. Now, why would I want to do that? Because all I need to know is what's secant of y. Secant is the reciprocal of cosine. Secant is which side over which side? Secant of y. Opposite over adjacent is cosine, right? So secant would be hypotenuse over adjacent, right? So I just need to take 1 and divide it by this. But what is this side? Well, you have to figure that out, right? You have 2 sides of a right triangle. To figure out the third, you use Pythagorean identity. So let's just call this side for now a. Do you agree a squared plus x squared is 1? Yes? I'm trying to figure out what a is. Subtract x squared on both sides. And then finally, a is what? Square root on both sides. Now, I should technically do a plus or minus here, but a is the length of a side of a triangle, so it's going to be positive. So my answer is square root of 1 minus x squared. So that's what a is, this side. So coming back to this, secant y we said was hypotenuse over adjacent. So y prime should be 1 over square root 1 minus x squared. Make sense? That matches the formula. Each one of those can be done the same way. So this set of formulas, pay attention to some of them have weird signs in them, like the derivative of the arc cosine is negative 1 over the square root of 1 minus x squared. The derivative of arc tangent, this one comes up a lot, especially in Cal 2. So I think I might take a moment to try and do that one. You know what? Why don't you do it? You want to do it? You want to work in groups? I'll let you do it. See if you can show that that's true. Okay? The third one. Verify that that formula is true. You're going to follow the exact same template that I just laid out right here. If y is equal to arctangent x, show that the derivative is 1 over 1 plus x squared. And just follow through doing exactly what I did, except, with tangent instead. That sound good? Go ahead. See how long it takes. When you or the people at your table get it, let me know. I'm not going to leave all this up here because if you weren't taking notes, that's on you. This is what you're trying to show right here, number 3. Formulas are out here now. Like I said, that just opens up what's possible now in terms of derivatives in chain rule. Any of these can be used with chain rule now. So let's see how we could implement some chain rule on these. So here's an example. Let's say I give you y is equal to the arctan of sine x, and you're asked to find y prime. Well, the first thing you have to realize is that this is composition. You have a function inside of another function, right? You have sine x is sitting inside of arctangent x, so arctangent x is the last function on the outside of the onion, right? So when we take a derivative, we start on the outside, we work our way in. So you have to ask yourself, what is the derivative of arctangent of something? What is it? Look at your formula sheet. What's the derivative of arctangent of x? 1 over 1 plus x squared, right? So the derivative of this would be 1 over 1 plus what, though? Not x squared, sine x, or sine squared x, however you want to say that. That's the first part. Does everyone see that? Derivative of arctangent of my yellow cursor is 1 over 1 plus my cursor squared. Then go inside, take the derivative of tangent x, sine x inside, which is cosine x. And so you could just slide the cosine on top and leave it like that. And that would be fine, just like that. How about something like this? Y is equal to e to the x arc sine x. Find y prime. So what do we have going on here? It's product rule, right? Everyone see that that is a product between the two functions? So the derivative would be, here's our product right here. I was still seeing on this last test a lot of people doing this, which is fine. So I'm going to do it this way. They were actually writing out like what they had to do. That's your product rule. Derivative of the first one times the second plus derivative of the second one times the first one. So what is the derivative of e to the x? Itself, right? E to the x times arc sine x plus what's the derivative of arc sine x? 1 over square root of 1 minus x squared times e to the x again. And you could factor an e to the x out of both of these. You could. But that's sufficient also. You see that all we're doing is we're just opening up the spectrum of functions that we know how to take derivatives of. We've got all the trig functions we can take derivatives of, all the inverse trig functions we can take derivatives of. We can take derivatives of log functions, exponential functions, polynomial functions, rational functions, and pretty much anything at this point, except hyperbolic functions. We haven't talked about those. Usually in Cal 2, you start with derivatives of hyperbolic functions. All right, how about another one? How about if y is equal to arctangent of x cubed? What's y prime? So 1 over 1 plus what? So arctangent's the outside thing happening here, right? This x cubed is inside the arctan. Even though I didn't put the parentheses there, it's implied. So what goes down here? X cubed, but then all of that squared, right? Am I done? No. Times the derivative of what's inside, 3x squared. So what you would have at the end of it is 3x squared over 1 plus x to the 6th. Now I'd like for you to compare that to the next one. Anyone still need that? Y equals arctan of x cubed. So what's the difference between this one and the last one? Yeah, the order of things is different, right? The last thing happening here is what? The last thing that we would be doing. Cubing. Cubing is the last thing, right? So if you were to plug a number in for x, the first thing you do is take the arctangent of that, and then after you're done with that, you would cube that. So if we're working backwards, we're going to cube is the last thing we do. That's the first thing we're going to do when it comes to derivative, right? This is not a product or anything. So the derivative here will be, well, we have this whole thing to the third. What's the derivative of something to the third power? 3 times that something, right, squared. Am I done? Times the derivative of what was in there, right? What's the derivative of arctangent x? 1 over 1 plus x squared. And, I mean, you could clean it up. You could just maybe write 3 arctan x squared all over 1 plus x squared. That would be fine. Questions? Okay, let's do one more. How about y equals 5 to the cotangent inverse of 1 over x? Do you see product rule? No? Nothing here is being multiplied, right? Do you see quotient rule? The only quotient I see is right in here. But I'm not going to do quotient rule for that. Composition? Function inside a function? Yes? So you have 1 over x is sitting inside of the cotangent, right? But the cotangent is actually the exponent of 5 to a power, right? Yes? You could. You could. You wouldn't have to in this case, but you could, yes. How about just a straightaway, like covering all this stuff up, What's the derivative of 5 to something? What's the derivative of 5 raised to a power? Okay, so we're looking back at, like, what's the derivative of 5 to the x? 5 to the x itself, ln 5. Remember that? That's derivative of a to the x is a to the x natural log a. So the derivative of 5 to this junk is 5 to the junk again times natural log 5. Am I done? No, now I need to go look at the junk. The junk up here is cotangent inverse of something. What's the derivative of cotangent inverse of something? So you go to your formulas there. What's derivative of cotangent inverse of something? Negative, it's just like tangent, right? But it's negative. Negative 1 over 1 plus that something squared. So it would be negative 1 over 1 plus that something squared. What's the something I'm going to square? 1 over x. Times, I'm not done, the derivative of what was inside the cotangent inverse. What's the derivative of 1 over x? Negative 1 over x squared. That's the same as x to the negative 1, right? Derivative of x to the negative 1 is negative 1x to the negative 2. Power comes down, subtract 1. Negative 1. Oh, after the derivative. Derivative takes you here. And then you could try cleaning this up, but it's a mess. That's the raw derivative right there. Any questions on that? Okay, for homework, I'd like for you to look at page 184 and just go through those are all pretty good. 17 through 29 odds. And then, yeah, that'll be good. All right, so end of the day, all that we've done is thrown in 6 new functions that we know derivatives of. And so throw it together with everything else we have, and now things can get really ugly, right? Really complicated looking functions. We can find slopes of tangent lines on them. All right, moving along. Look, this topic is so critically important. It's one of those things that if you do continue and do math, it creeps its little head up in little places that you least expect. Well, you'll be in a class and the instructor will just be like, oh yeah, just use Lhopital's rule there. So you say that Lhopital, 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 Lhospitals is the way it's spelled, right? Lhopital. Lhopital. Okay. Um, I don't know. I'm sure the book says who talks about Lhopital somewhere. Let me see. I used to know a lot about him. L'Hopital's rule is named after French nobleman Marquis de L'Hopital. 1661 to 1704 is when he lived, but was discovered by the Swiss mathematician John Bernoulli. Who's that? All right. Anyways, this is an awesome, awesome rule. All right. And I think before we talk about it, we've got like 30 minutes left, I want us to talk about like where we're headed with this, because you're not going to like it when I say it, but please just bear with me. Remember limits? Remember limits? And the limit was like the beginning of this class. We started with the limit idea. And it was always about you're letting something get close to something, and then what happens to something else. So we had something like I don't know, limit x would go to like 2 of x squared minus 4 over x minus 2. So we know right now that if you just plug 2 in, right, if you plug 2 in, or try to plug 2 in, the form that we got when we did this was 0 on top and 0 on bottom. And we always said that that was bad. Remember me saying that? That was bad, and that we wanted to somehow do some algebra to try and figure out what's going on, right? So the algebra we would have done in this case was we would have noticed the top is a difference of squares. We would have rewritten this limit. X approaches 2. It would have been x plus 2, x minus 2 over x minus 2. Then the x minus 2's would have canceled. And then when we let x approach 2, we get 2 plus 2, and the answer is what? 4. So what we know is that even though you cannot plug 2 in, we are aware that the closer and closer you get to 2, the closer and closer this expression gets to 4. And we handled it, that bad situation, we handled it with algebra or trick. Remember, sometimes we did conjugate, all these different things, right? Okay, so what I want to start with here is getting us thinking about limits again. I want to talk about what situations are bad. We already know a few of them. So what are the bad situations? What are bad, quote, bad situations? Let's not talk about, your personal life. I'm talking about limits. What are bad situations? We already know anytime we take a limit, so I'm going to put here so you don't confuse us. In the limit, if we get any of the following, it's a bad situation. I have to put here in the limit because, well, let me put the first one. 0 over 0. Look, 0 divided by 0 is undefined, all right? It's totally undefined. But if you're taking a limit and you're getting 0 over 0, that is a form of a limit, right? So that's why I'm saying in the limit, if we get this, that's a bad situation. What was another bad situation we would have? Something over 0. Do you remember when we had fixed over 0? That gave us, but that always gave us one of 3 answers, didn't it? It was either infinity, negative infinity, or does not exist, right? So that usually didn't require any algebra. We're not going to call that a bad situation. There's another one that required some trick. Infinity over infinity. That was the one, like the first example I ever gave you of that was where you had like, you had to multiply top and bottom like 1 over x squared and pass it through. You can refer to your notes. All right, infinity over infinity. Top's growing, bottom's growing. Who wins? Another bad situation. Minus infinity, yes. That was a bad situation. Because one thing's getting big, the other one's getting big. Who wins, right? These are all bad situations. There's a technical word in mathematics for bad situation. I'm saving it, okay? I'll tell you what it's called in a second. Next one, I'm trying to think of what we did. 0 times infinity, good. 0 times infinity. And that could have been infinity times 0 or 0 times infinity, or it could have been negative infinity times 0. It's all the same. That would be a bad situation. Any others? Okay, not everything though. It's got to be specific. If 0 is raised to the infinity, is that a bad situation? Don't write that down. Is that a bad situation? Think about what's happening. The base is wanting to become what? Small, right? And then the exponent is getting bigger. What happens if you take a small number and raise it to a power? Does it get bigger or smaller? Smaller. So it actually goes to 0 faster. So that's not a bad situation. That's actually a good situation. So let's put below here, while we're doing this, let's put good situations below this, meaning things that we could figure out without having any issues. One of them that was mentioned, let's see, 0 to the infinity right there. Infinity plus infinity would not be a problem for us. That would just be infinity. Fixed over 0 is not a problem because that's one of the 3 different possible answers. Another one would be fixed over infinity. What does a fixed thing over infinity go to? 0, right? So all of these are good situations. I'll put good out here. Okay? If you get a limit that one of these is happening, you know the answer. Getting back to this though. 0 to the infinity didn't work. 1 to the infinity does. Because what's happening here is the base is trying to become 1, getting closer to 1, while the exponent is getting bigger. When you take a number that's a little bit bigger than 1 and raise it to a power, it tries to get bigger. But then the base itself, if it is 1, 1 to any power is 1. So it's like a tug of war. Who wins? Don't know. Anything else? How about infinity to the 0? What does anything raised to the 0 want to become? 1, but infinity wants to become infinity. So that would be a bad situation. Can you think of anything else? 0 to the 0 would be a bad situation. For the same principle, the exponent wants to turn it into, right, 0, anything to the 0 wants to become a 1, but 0 to any power should be 0, so who wins? Anything else? 0 over fixed? Yep. Infinity over fixed? Is that what you're saying? Oh yeah, 0 over infinity would work. But so would infinity over fixed. These are all great things. These aren't going to happen on a test, but let's just recognize when we have a good situation, right? I guess the thing is when you're first looking at these different situations, you might think, well, just anything I can think of is going to be a bad situation. No, it's only certain ones are really bad. Anything else we can think of? Okay, so what would happen with that? Is that a good or a bad situation? Infinity to the infinity. Good. Because the base wants to become big, right? Take a big number, raise it to a big number, it's going to get big even faster. Anything else? Okay, so that would be, we could just rearrange it and it would be that, right? Okay, let's just go with this as our list. And if we run into something later, we'll just think about it and we'll say, is it good or bad, right? Okay, these are called the indeterminate forms. So if we are ever taking a limit and we get one of these situations, we cannot determine what the answer is easily, right? Like we have to do some algebra or some trick. Do you agree? Since we cannot determine what they are right away, they are called indeterminate forms. And up to this point, we've done our best to try and handle these situations. But we've also seen how ugly it can get. And then here comes Lhopital. And Lhopital has a rule that is going to make a lot of this trivial. It's a great result. So here it is. Lhopital. I have this little chant that I do with Lhopital, so I don't know why. In fact, I had a student tell me one time, because we actually, believe it or not, are offering Cal 1 as an online course where they basically watch all the videos that I've told you about, and then they watch all my class videos, and then they do all the homework. And I've got this, what's that? They have electronically, or they call me or something like that. But this one student emailed me, and he was like, I've been chanting your Lhopital chant lately or something. Whenever I'm using Lhopital's rule, you'll see. I always just like to, Lhopital, I don't know. It's fun. Well, it's about the same. Yep. Yeah. The problem with the online one is that they do their homework online, and so it's a computer, and they think they're doing good because they figure out like the little weaknesses in the computer, and they're like, oh, that's just the same problem I just did, except they changed a number, so I know the answer is only going to change by a number. They don't really know what they did. So they do real well on the homework, and then they take the test on campus. They have to do a paper pencil test. Yeah. So anyway, okay. L'Hopital's rule. So here it is. It's very simple rule. If you're taking a limit, and it really does not matter what it is that you're taking the limit of, it really does not matter what it is it's going to. Okay, so it could be x is going to 2, x is going to infinity, t is going to 5. It doesn't matter. Who cares? You're taking a limit. And what you have is on top you have a function, and on the bottom you have a different function. So you have a quotient of two functions, something divided by something. If this limit goes to 0 over 0 or infinity over infinity, either one of them, and I'll also throw on here, does not matter if these are plus or minus. So you can have infinity over negative infinity, you could have negative infinity over positive infinity, you could have negative over negative, positive over positive, does not matter. 0 over 0 or infinity over infinity. If that happens, then the limit, okay, whatever it is, that limit you're trying to find, okay, so all I did is just rewrote this, is equal to the limit as whatever goes to whatever, that doesn't change, if it exists. That's the rule. That's it. Now, what is the rule saying? That's right. It's saying if you're trying to find the limit of a quotient of two things, and it's giving you this one of those two bad forms, one of those two indeterminate forms, if that's happening, then the answer to what you're trying to find, you can also just, instead of taking the f and the g and trying to figure out what that's becoming, take the derivative of the top, divide it by the derivative of the bottom, and figure out what that limit is. And you're not doing quotient rule. Okay? So that's one of the big mistakes students will do with Lhopital's rule. They'll be like, oh, I got to do quotient rule. No, this is the one time you can violate the quotient rule. Derivative of top over the bottom. Derivative bottom. That's it. So that's the rule. Okay? Here's it in practice. Example. What is the limit as x approaches 2 of x squared minus 4 over x minus 2? We just did that problem, right? What was the answer? It was 4. Okay? Let's see if this falls into Lhopital's rule. What happens when we do the form? We know we get 0 over 0, right? This gives us the form 0 over 0. So Lhopital's rule is valid. We can use it. So I'm about to use it. So I'm going to say, okay, this then is equal to the limit as x approaches 2 of the derivative of the top, which is 2x, over the derivative of the bottom, which is 1. And now just try and plug 2 in. And what do you get? 4. And you're done. Now, there's a little thing that we use. There's a common notation that we use to let people know, like from this step to this step, I used Lhopital's rule, didn't I? I'd like to make a note of that so that people know that's what I did. Different books do it different ways. A lot of books will put an H over the equal sign that lets everyone know I used Lhopital's rule. I've never adopted that. I've always, I don't know why, I've always put an L and I've always circled it. That's my own notation, but feel free to use that or use an H, just as long as you somehow signify that you use the rule. Okay? That's pretty awesome, isn't it? Let's go back. Let's take a look at, how about this one? What about limit x goes to 0 sine 5x over tangent pi x? Okay, what form do you get here? So let x go to 0, you get 5 times 0 is 0, sine of 0 is 0. So you're getting a form on the top of 0. On the bottom, 0, tangent of 0 is 0. So you're getting the form 0 over 0. Lhopital's rule is okay to use. Now, let's go and just take a second to remember how we used to do it. Do you remember me doing that? You peel it all apart, and then you try and use this thing where you're trying to get sine of junk over junk. So you have to introduce this like 5x on top and bottom and slide it over. Do you remember me doing all that? It was like this weird voodoo magic stuff we were doing, right? Remember? Okay. No more. So this should, by Lhopital's rule, be equivalent to the limit. Oh. Who said that? Okay. So what is the derivative of sine 5x? And be careful here. It's cosine 5x times 5. Don't forget the chain rule, right? You have to take derivative of what's inside. Over, now the derivative of the bottom. What's the derivative of tangent of something? Secant squared of pi x times pi, because the derivative of pi x is pi. Now let x go to 0. These are constants, yes. So now let x go to 0. 5 times 0 is 0. Cosine of 0 is 1. 1 times 5 is 5. So the top is going to 5 over. Okay, secant is the reciprocal of cosine, right? What is then secant of 0? What is secant of 0? It's the same as 1 over cosine 0, isn't it? What's cosine 0? 1. So 1 over 1 is 1, and then square it. 1 times pi, and you get pi. 5 over pi. Much easier, right? One more, and then we'll address the question that I heard kind of under someone's breath over there, because I have a good answer. What form do we have here? Where's the numerator headed? Infinity? Where's the denominator headed? Infinity. Is that okay for Lhopital if we have that? Infinity over infinity is okay. So we're going to do Lhopital's rule. Limit x goes to infinity. Derivative of the top, 3. Now be careful here. Derivative of the bottom. What is the derivative of the square root of something? Chain rule, right? So first 1 over 2 times the square root of that something. But then times what? The derivative of what's inside, which is 2x. That actually didn't turn out to be very nice, did it? I mean, like, the last one, things got kind of easier. Let me clean this up a little bit. I'm not doing anything, I'm just cleaning it up. Those 2's canceled. And so I have 3 over x over square root of x squared plus 4. And can you rewrite that? Yeah, you could rewrite that as limit x goes to infinity of 3 root x squared plus 4 over x. Did that help? What happens when we let x go to infinity? On the top you get infinity, on the bottom you get infinity again. That didn't really help, did it? So let's think through this. If we just totally ignore everything else we've done, all right? So forget that all of this has ever happened, and this were the problem that I started with, then you could use Lhopital's rule, couldn't you? Like if I just say, hey, this is a limit I want you to figure out, you would say it has the form infinity over infinity. You'd say it's valid for Lhopital, and you would use Lhopital, wouldn't you? So in other words, what I'm saying is we could use L'Hopital's rule again, couldn't we? Just try it again. What's going to happen, though, is not good. So what I'm doing is I'm applying L'Hopital a second time. Derivative of the top. I'm going to just tell you what it is rather than working it all out. That's the derivative of the top over the derivative of the bottom, which is 1. And so what you're back at, again, is infinity over infinity. And what you are is stuck in a loop. You're just stuck in a loop. In other words, L'Hopital's rule, as great as it is not the magic pill. You would have to do this one the way that we did when we first were introduced to it, which was, does anyone remember how to do this one? Look at the highest power of x in here. Try and get it to go away. So you'd have to come in with a 1 over x on top and bottom here. 1 over x, not 1 over x squared, because when you go 1 over x and you push it in the root, what happens to it? Squares on its way in. That's how you would do that one, and L'Hopital is no help. Okay? So although it's great, it's not after you try it a few times. Yep. So I would say stuck in a loop here. Stuck. Okay, so we'd have to just stop. I will answer the question in a second. No. Sometimes it's tough with L'Hopital because sometimes you can. It'll eventually happen. What I would hope you would notice here is the first time you did it, right? You had a linear expression over a square root of a quadratic, right? You did L'Hopital once. You turn up with the square root of a quadratic over a linear. Then you do it again, and you turn out with the linear over the square root of a quadratic again. That's what the original one was, right? Linear over square root of quadratic. So if you do it again, you're going to wind up probably with square root of quadratic over a linear. And then you'll go backwards and keep flipping back and forth. So you're going to go nowhere. How about this one? Limit x goes to infinity of x to the 1 billionth power over 2 to the x. X to the billionth power. So what happens if you let your x here, your base, get big? What's a huge number raised to the billionth power? A huge number, right? That's infinity. That's headed to infinity. Then what's 2 to a huge power? What the heck happened? Where did my 2 go? Now it just came back. Weird. Okay. What's 2 raised to a huge power? Infinity also, right? Who's going to win here? Which of those do you think gets bigger faster? X to the billionth power or 2 to the x? 2 to the x? You think 2 to the x grows faster than x to the billionth power? All right, well, let's see. If you plug in, let's just plug in 2. Right? Let's not even try and plug in a big number. What's 2 to the 2? 4. What's 2 to the billionth power? On your calculator, overflow. I mean, your calculator can't do that number. It's too big. Right? Now, let's try 3. 2 to the 3 is 8. 3 to the billionth power? Right? But eventually, what happens? It passes it. eventually 2 to the x gets bigger than this. Now, it happens way out there, but it does. And here's the way to prove it. To prove that this is actually going to get bigger faster than this is to show that this limit is going to go to 0, which means that the top is they're both getting big, right? But eventually the bottom gets bigger so much faster it squashes the number down to nothing. So let's see if it's true. L'Hopital's rule tells us what? We can take the derivative, top and bottom. What's the derivative of x to the billionth? 1 billion x to the 999999999 all over, what's the derivative of 2 to the x? 2 to the x, natural log 2. So we did L'Hopital's rule one time. Now let x go to infinity. What do you get? Infinity to the 999 millionth power, right? Is going to be infinity? Yes? Okay. Over 2 to the infinity is infinity. So we still have infinity over infinity? Are we stuck in a loop? Is this a loop or not? What happens every time I take a derivative? On the top, what happens? This power comes down 1, doesn't it? Does this change? All that keeps getting tacked on is a natural log 2, natural log 2. So if I keep repeating this process another 999 million times, eventually this up here is going to become a constant, isn't it? Because the power keeps coming down. Eventually it'll be x to the first power. And the next time I take the derivative, it'll be derivative of x is 1. And then the top will just be a constant, won't it? And the bottom will be 2 to the x with a bunch of natural log 2's. And so you'll have a fixed number over infinity, eventually, which goes to 0. So with repetition, repeat this until you get to this. Limit, x goes to infinity. You'll have a bunch of junk sitting in front of x to the first power, right? Eventually. All over 2 to the x times a bunch of natural log of 2's. Natural log 2, natural log 2, da 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 da. Everyone understand that this junk out here is just a number? It was like that 1 billion that came down. The next one that would come down would be 999,999,999. So you'd have all this stuff. And now the next one through, your numerator would be a fixed number, and your denominator would be 2 to the x times natural log 2, dot, 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 and that goes to 0. Does that make sense? I mean, you would never repeat it that many times. This one would be done just by a process of just thinking through it, like seeing the pattern. So we've seen, is it time to go? L'Hopital's rule can be very helpful. It's not the ultimate answer, and sometimes it has to be repeated more than once. I will answer the question. Why did we not do L'Hopital's rule from the beginning? This is an important concept. Think about this. The way the course started, all right? It's not because we're trying to be mean. The course started with the idea of the limit, right? And we tried to do these limits, and I tried to show different ways. Then after we studied the limit, we defined the derivative of a function to be the limit as h goes to 0 of f of x plus h minus f of x all over h, right? How am I supposed to, in the beginning, help you do limits using L'Hopital's rule if you don't know what a derivative is? Right? So you can't get the carriage in front of the horse, right? You have to get the carriage behind the horse. So once we find the derivative, we come back and we say, we can use the power of derivatives to help us do limits. So there's a reason why we didn't do it. Okay, I will tell you for homework, you should look at page 197. This is not the entire assignment, just to get you warmed up with this. Okay, 1 through 21, sorry. 1 through 21 odds. That should be enough to get you going with it. But there's more.